Hello and welcome to this video on how the resin used in 3D printing works. If you want to get fine results when 3D printing, filament just isn't up to the task. The solution at present is resin printing. This method is far more accurate for details and intricate features. This is because resin works very differently. To understand what is happening, we need to give an overview of what resin printing involves. Well, strictly speaking, masked stereolithographic printing. It involves the use of a reactive resin held in a vat with a clear base. Under the vat is a screen. Often it is an LCD screen, but the exact light source varies slightly. This shines light up through the base of the vat and it hits the resin in a pattern specific to a layer in the print file. The resin will react to this and harden. The printed resin layer is then raised and pulled away from the base. This allows fresh resin to flow in underneath, and the process is repeated layer on layer until the print is finished. The important part to all of this is how the resin reacts and how it works. Many of the resins used, particularly when we're talking about hobby-grade printing, are polymers, or at least they will be after the reaction's finished, polymer being made from the Greek words for many and parts. It is nearly always a substance consisting of relatively large molecules, repeating consistently in subunits. This means you get something very similar to a Lego brick that is assembled into the form of your end product. Most of the examples applicable to this video are going to be something like methyl acrylate based resin systems. On that basis, we'll focus on that example, but to be honest, most of them will have a very similar method of activity if it's not specifically the same. Methyl acrylate becomes polymethyl methyl acrylate through polymerization. Polymerization is taking individual parts and assembling them into a long chain of parts. It works because about 100% of the light beyond 300 nanometers is absorbed. Also, the methyl acrylate itself is very soluble in most organic solvents. This means you can get it, turn it into a liquid, store it relatively stably, and then in a controlled environment react it. This is also why most resins use a wavelength between 350 nanometers and 415 nanometers. This is the right wavelength or range of wavelengths to activate the resin and various other compounds within it. With methyl acrylate, it's enough to excite the electrons in the bottom carbon here. That leads to the double bond breaking, and now you have a free space for an electron to do something. With 4 possible connections, it allows you to create a series of repeating units using the now free 4th electron space or slot. Of course, this makes not only a very solid but brittle and heavy resin product. It's also why other ingredients are often used. One of the major ingredients is a photoinitiator. This is another molecule that will cross-link with other compounds and is done by free electrons that create covalent bonds. You need not only these 2 products but a series of others to provide other features, like elasticity, to ensure that you have as much opacity as possible, to give the right amount of tensile but also strength to the thing you're trying to make. There are a range of other products like dyes you want to have suspended consistently throughout the resin as well. All of these will have effects on the exact nature of what you're working with, but in general, the photoinitiator acts as a second layer of, let's say, security, where it helps to cross-link more compounds and add a second mesh to the entire product. By having 2 different systems at play, you can ensure you get maximum binding of everything, but you won't have everything bound right away. That's just the first step, and it finishes when you take your print from the printer plate and put it into a curing station. Often you'll be using something like UV light in a curing station, like a resin wash and cure station. This finishes the job by cross-linking other resin products that are not reached during the printing process, or in some cases, products that aren't reacting to the light wavelengths that were used. This further adds rigidity and strength. It's useful not just because you have the ability to actively control the reaction, but you have the ability to have the initial work done, which is the most technical and difficult work, but then to be able to leave it to set and react further, meaning you don't need all the extra specialized reagents, light, and technicalities in the machine to make it work. There are resins that are not readily available or only in early development that also include a photoinhibitor. This is a molecule that prevents reactions to certain light wavelengths, and it can be useful if you're attaching it to certain molecules within the resin. It allows you to control which of them react when and how. So for example, if you want something that responds to UV light but not blue light, or you want blue light to be able to stop a reaction from occurring, you can mask everything going on with the blue light and only have the red light in the places you want it. This ensures that you get a solid and complete block of any reaction where you do not want it to happen. This will also prevent runaway reactions where everything starts to bind together, and at least in theory prevent you from getting a blob. In short, a normal reaction is like taking a box of Lego bricks and throwing them together with glue, shaking it until the blocks line up, and hoping that everything works. With SLA printing or MSLA printing, you can fit each brick together tightly, removing the need for not only glue but force, because only those things you want have been put where you want them. More importantly, you're able to make it so that they eventually fuse together without having to apply any extra effort. Thank you for watching this video. If you have found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions you have below.